Can't find my way home. Leave your body alone. Somebody hold me. You are the reason I've been waiting so long. Somebody hold me. 'Cause I'm you are the reason I've been waiting so long.
Hi, Nicholas is asking a nice question here. Can we say that the function is flat at one point if and only if the gradient of the function at that point is a null vector? I don't think you can say that. And the nice counterexample is a plane. Right, take a plane. I mean, I think everybody will agree that a plane is flat. And the gradient is not the null vector. Right? This is going to be flat at every single point. So I don't think that works. Yesterday we showed that the gradient is normal to level curves. Let's do the same thing today. We're going to show that so you meant that the derivative is 0, so flat in that sense. Well, you say. So, I mean, what you're really suggesting is that at that point, well, I mean, now you say no change. And that's a bit problematic. Because think about the Cal 1 counterpart. So here we're going to have a derivative of 0. But when you move away from that, the function does change. So I mean, we have derivative 0 just at one point. Now, in fact, we're going to see today that this idea extends to higher dimensions, right? And here we had a notion of critical points, and we're going to have that same notion in higher dimensions. And we're going to see that today. I've prepared that, time permitting. I don't know if we're going to have time to do everything, but I mean, it's coming up. If not today, then tomorrow for sure. But in the meantime, let's prove that the gradient is normal to level surfaces. Right? Yesterday we proved that it was normal to level curves. Now we're going to prove that it's normal to level surfaces. And if you have a level surface, if you have a level surface, imagine solving for z, right? I mean, perhaps implicitly under the assumption that df dz is not zero, right? The implicit function theorem suggests that you might be able to solve for z as a function of x and y. And in that case, the normal is going to be minus dg dx minus dg dy and 1, right? We saw that. We saw that when we were defining the tangent plane. So this is going to be the normal, or if you prefer, dg dx is dz dx. So minus dz dx minus dz dy and 1. This is the normal. Well, now let's go back to this and let's take the gradient. What is the gradient here? The gradient of f is df dx, df dy, df dz. And let's work out dz dx using this equation here, right? If we have f of x, y, z equal to c, and if you differentiate the whole equation with respect to x, assuming x and y are independent variables, and z is a function of both x and y, what do we get? Well, we get f1 plus f3 dz dx by the chain rule. And this is 0. So dz dx is easily seen to be negative f1 over f3. And if you do the same by differentiating with respect to y, if you differentiate with respect to y instead, well, this is f2 times dy dy, which is 1, plus f3 dz dy. And that is equal to 0. And so dz dy is negative f2 over f3. So your normal, which was minus dz dx minus dz dy and 1, is now easily seen to be f1 over f3, f2 over f3, and 1. And if you multiply this by f3, you get f1, f2, f3, which is exactly the gradient. So this is really a multiple of the gradient. And so this is going to be parallel to the gradient. The gradient is normal to the level surface. Convinced? How are we doing here? take a few examples from the book, taken from page 1005. We are asked to find the maximum rate of change and the direction in which it occurs. Where your function is x over x squared plus y squared at the point 1, minus 1. All right. So you'll recall yesterday we saw that the maximum rate of change of the function occurs in the direction of the gradient. So the gradient of f, derivative with respect to x, this is a quotient, so quotient rule applies. vu prime minus uv prime all over v squared. And the derivative with respect to y is easily seen to be minus 2xy over x squared plus y squared all squared. So the gradient at the point minus 1, 1, if x is minus 1 and y is 1, this is going to be 0. So 0. And 2 over 4, 1. So the maximum rate of change occurs in the direction of the gradient or in the direction of 0, 1/2. And what is it? What is the maximum? So this is the direction, and the maximum rate of change we saw to be the norm, which in this case is just 1/2. We want to do another one? All right, consider this. Same question, right? Find the maximum rate of change and the direction in which it occurs. And I mean, it's the same idea, right? the maximum rate of change occurs in the direction of the gradient. So let's work out the gradient. And the gradient at the point is what? This is log 1, which is 0. This is 1/2. And this is 2. So maximum rate of change occurs in this direction. And what is it? Uh, 17, 2/17. Is that correct? How are we doing? Still so few people. Well, that's what we said yesterday. We said that yesterday. If they were writing it yesterday, they're not writing it today. Yes, thank you. I've made a terrible mistake here. I don't know why I have that. It is root 17/2. Thank you. Absolutely. Yeah, that's why I wanted the midterm on the weekend. And if I had been informed of that 72-hour rule, I would have opened it up Friday. So we would have done it, Saturday, Sunday, Monday kind of thing. Yeah, it's gonna be something. It's gonna be something. Going back to in-person lectures without anything recorded. I don't know. We'll see. I mean, it's always asking if, Nicholas is asking if classes with more than 150 people will still be online. That's what's been announced. I mean, I don't have any more information than you do, but that is what has been announced. I suspect that they made an announcement. Well, first of all, I mean, they require everybody to be back in Montreal so that they can attend regular classes. I strongly suspect that the beginning of class may be online, but perhaps around October, if everybody has a second dose of the vaccine, I suspect that, anyways, at some point along the semester, I think everything's going to come back to normal. At least that's my hope. Again, I have absolutely no information. I just suspect that that's what's going to happen. How do we get the distance? The norm. The norm is the square root of the sum of the squares of the components. I mean, I don't think we're going to have much say or opting in or out. I don't think that's going to be an option. We'll see. We'll see. But, I mean, the vaccination is going well in Quebec. I mean, we're coming up to 50% of the people vaccinated. So, and I mean, I just read that restaurants may be reopening, at least outdoor dining. So, good for you. Good for you. I got mine on Tuesday of last week. So things are looking good, I would like to believe. All right, what do we want to show here? Here we want to prove that the gradient is linear, right? Think of the derivative. The derivative of a sum is the sum of the derivatives, and the derivative of a constant times a function, you can pull the constant down. So this is really proving that the gradient is a linear function. A very, very, very easy thing to prove if you know what you're doing. If you don't, then you're in trouble. So U and V are functions. Did I say vectors? I meant functions. Sorry about that. U and V are functions, and A and B are real numbers. So this is essentially like the linearity property of the derivative. Let's prove it. So what is the gradient of this? Gradient of this is the derivative with respect to x of AU plus BV, the derivative with respect to y of AU plus BV, and more if you have it. Let's just say ... It could be could be a function of just two variables. There could be a z and there could be others. But normally if you prove it in the R2 case, that's good enough. So what is the derivative of this with respect to x? Well, a is a constant. So this is just a ux plus b vx. Here, again, a and b are constants. This is a uy plus b vy, and so on and so on. And now you can break it up just with the u's and with the v's. So this is AUX, AUY, and so on, plus BVX, BVY, and so on. And now pull out the A. So this is UX, UY, and so on. And pull out the B from the other one, VX, VY, and so on. And you recognize this as being the gradient of U. And you recognize this as being the gradient of V. And that's it. Let's do another one. The gradient is the gradient of an ordered set or a vector. It's a vector. It's a vector, right? I mean, we've done two examples. We were getting vectors here. The gradient of a product, UV, is V gradient of U plus U gradient of V. So it's essentially a product rule for the gradient, right? The gradient follows this product rule. Let's prove it. And the proof follows immediately from the product rule for functions. What is the gradient of UV? Well, this is the derivative with respect to x of UV, the derivative with respect to y of UV, and so on and so on. How do you differentiate UV with respect to x? Well, now this is a product. So product rule applies. Differentiate the first one, leaving the second one fixed. Plus leave the first one fixed, differentiate the second one. And same for the other one. Differentiate the first one, leaving the second one fixed. Plus leave the first one fixed, differentiate the second one. And so on. And again, do exactly what we did. Split it up with the u's. So the derivatives of the u's. And those where the u's are stay fixed. And here, if you factor out a v, this is ux, uy, and so on. And here, if you factor out a u, this is vx, vy. And you recognize that this is the gradient of u. And you recognize that this is the gradient of v. And there you have it. Exactly what you wanted to prove. How are we doing here? Questions? Why can we factor a function out of a vector? convince yourself via an example. Suppose we had worked out that the gradient of some function was xy squared 2x sine x and what? X squared z. Let's just say. So suppose we had worked out that the gradient of some function was this. What does this mean? This means that if you take any point in x, y, z, right? So take any point, whatever, take any point 2, 1, 3. If you take any point 2, 1, 3, then you can work out the gradient at that point. Right, and what is the gradient at that point? It's going to be 2, 4 sine 2, and 4 times 3 is 12. Right, so if you take any point, you're going to get the gradient at that point, which is the direction of fastest increase. But now, in here, it's clear that you can factor out a 2. Right? You have no trouble factoring out a 2 because you understand that 2 times this vector gives you that back. But that's exactly what's happening if you factor out an x. Right? If you plug in this point into here, x is 2, so you're going to get exactly that. Right? The x is a function, but it really represents a point. So yes, you are factoring out functions, but it's equivalent to factoring out real numbers. Because in the end, x represents exactly that, a real number. Find the equation of the tangent plane and the normal line to all right. You have options. What are you going to do? right? As Shiyan suggests, we know the gradient is normal to level surfaces. Now, immediately, we don't have a level surface here. Not immediately, but we can adjust. If you bring the 3x squared y squared z squared to the other side, then you recognize that this thing is actually a level surface to that function. And it's very important to realize that. Right, so you have a level surface here for that function. So the gradient is normal to the level surface. Gradient is normal to the level surface. Gradient at the point 111 is what? 4 minus 6 is minus 2. Minus 2 minus 2. So your tangent line minus 2x minus 2y minus 2, not tangent line, tangent plane minus 2x minus 2y minus 2z is equal to d, and it has to go through the point 111. So d is minus 6, or if you prefer, x plus y plus z is equal to 3. And the normal line right, namely the line through the point 111 with direction vector minus 2 minus 2 minus 2. So going through the point 111. There it is. Questions? How are we doing here? We're good? Moving on? Let's move on. Let's move on. Thinking back to Cal 1, what did we do once we've defined all we needed with differentiation, we started looking, couldn't the direction vector also be represented 1, 1, 1? Absolutely. I just left it as -2, -2, -2 because I didn't want people to get lost, but absolutely. There it is. I mean, the 1, 1, 1 is very misleading because it's also the point 1, 1, 1, and I don't want anybody getting the false impression that we're using the point when in fact we are not. We are using the gradient itself. So in Cal 1, after differentiating, what did we do? We started looking at applications, in particular, maximizing and minimizing functions. We're going to do the same thing here. Definition. A function f of xy has a local maximum at the point AB if for all xy in a disk centered at AB, in a disk D centered at AB, f of xy is less than or equal to f of AB. Okay, that's it. So exactly the same definition as in Cal 1, right? In Cal 1, what did we want? F has a local maximum at A if in a small interval around A, F doesn't get any bigger than what it is at A. It could eventually get larger somewhere else, but if you're very close, that's why it's called local, right? If you stay close to A, then the function never gets larger than what it is at A. Here, geometrically, it's the same idea. Just one dimension higher. So you have this point AB, and you have your function. Well, all right, maybe a bad function here. Right, so anyways, what we're saying is, so you have some sort of bump here. In other words, if you stay close enough to AB, your function never gets larger than what it is at AB. And of course, local minimum similarly. Right? The point is the function could get larger elsewhere, but locally, you're good to go. Now back to the Cal 1 scenario. We saw that if a function was differentiable at A and it had a local maximum or a local minimum, then the derivative had to be 0. And this came to us via a theorem known as Fermat's theorem. Fermat's theorem tells us that if you have a local max or min at a point where the function is differentiable, the derivative has to be 0. And this gave rise to the notion of critical points. We have exactly that same theorem here. Theorem. Let f of x, y let f of x, y have a local max or local min at the point AB if the derivatives exist, if the partial derivatives then they have to be 0. And let's prove it, because the proof is very nice. And it is a simple application of Fermat's theorem. Can they not exist and you still have a critical point? Yes, absolutely. 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 And so that defines the critical points, right? If the derivative exists, it has to be 0. And so we define critical points to be points where the derivative is 0 or the derivative does not exist. And we're going to do exactly the same here following this theorem. Absolutely. Observe. So suppose f has a local extrema, either a local max or a local min at AB, and we're going to fix y equals b. Fix y equals b and consider f of xb. This is now a function of only one variable. This is now a function of only x. Right? So let's call that g of x. This is now a function of only one variable, x. And g has a local max or a local min at A. Right? Because f of AB is either a local max or a local min. So g of x has a local extremum at A, and so g primed of A must be equal to 0. by Fermat's theorem. But what is G prime of A? Well, what is G prime of X? There's only an X here, so this is F1. And G prime of A is F1 of AB, which is Fx of AB. So that has to be 0. So Fx of AB has to be 0. And similarly, you can repeat the same argument by fixing x equals A and getting the derivative with respect to y has to be 0 at the point AB. Very nice and slick, right? You're bringing everything back down to the one-dimensional case. So let me say this, Fy of AB equal to 0 similarly. And again, this motivates the following definition in the same way that Fermat's theorem motivated the definition of critical points. Definition, given a function of two variables, the point AB is said to be a critical point of F if Fx of AB is equal to 0 and Fy of AB is equal to 0, or if one of these does not exist. Convinced? Right, so critical points, essentially the same definition as Cal 1, where the derivatives are equal to 0. So we need both. We need both to be equal to 0, or one of them to not exist. Exactly. Yeah. Now, following, we don't need both to not exist, correct? As long as one does not exist, you're still going to have a critical point. Now, in Cal 1, following this idea of critical points, we were able to classify them, right, using a first derivative chart. Because a derivative bigger than 0 implied the function was increasing, derivative less than 0 implied decreasing. So, we could figure out if these were local max or local min, or possibly nothing. However, here, since we only have the partial derivative with respect to x and with respect to y, we don't have enough information, right? Because you can approach any point from infinitely many directions. So Nicholas is saying, so f of xy equals to 0 only contains critical points. I'm not sure what you mean here. Right, critical points are where the derivatives are 0. Right, and so what I'm suggesting is that a first derivative chart is not going to be possible here because you can approach points from infinitely many directions. So we're not going to be able to represent that in a first derivative chart. However, we had another approach in Cal 1. We had a second derivative test. And luckily for us, we also have a second derivative test available to us here to help us classify critical points. So let's state it. Second derivative test. Suppose the second partial derivatives of f are continuous. In a disk centered at AB. Where the partial derivatives are equal to 0. So AB is a critical point, but not any critical point. It's a critical point where both of the derivatives are 0. Both of the partial derivatives are 0. Let D be second derivative with respect to x times second derivative with respect to y minus this mixed partial squared. Right? I mean, let me bring your attention to the fact that we are assuming continuity of the second derivatives. So in a disk, so Clairaut's theorem guarantees equality of the mixed partials. So that's why you only have fxy and not fyx. You know they're the same. One, if d is bigger than 0 and fxx is bigger than 0, then f has a local minimum at AB. If d is bigger than 0 and fxx is less than 0, then f has a local max at AB. And finally, if d is less than 0, f has a saddle point. AB. How are we doing? Well, so that's certainly the question, Adam. Thank you. What is a saddle point? Let's take an example. Consider the function. I have never defined a saddle point yet. So the best way to do that is to take an example. Let's consider this example. X squared minus y squared. Let's find the critical points. So let's look at the partial derivatives of f with respect to x and with respect to y. These are 2x and 2y respectively. Nicholas is suggesting an inflection point. That's not quite, well, yes and no. I mean, we'll see. We'll see. We'll see. This example will illustrate beautifully what a saddle point actually is. So what are the critical points here? This is 0 when x is 0, and this is 0 when y is 0. So 0, 0 is the only critical point. And it's a critical point where the derivative with respect to x is 0 and the derivative with respect to y is 0. And that's important here, right? Because that's what we want in order to use the second derivative test. Let's look at fxx, which is 2, fxy, which is 0, and fyy, which is 2. There's a big mistake here. This is, of course, minus 2. Minus 2y and minus 2. Right? Did everybody pick that up? Minus 2, yes. It is, thank you. Thank you, minus 2y. Minus 2y, so there it is. So d, which is fxx, fyy, minus fxy squared, add the critical point. What exactly is d defined like that? It's a valid question. And another excellent question is, how does this extend to 3 dimensions or higher? And does it? And indeed it does. Indeed it does, through a matrix called a Hessian matrix. Which is the determinant of the second partial derivatives, right? So, I mean, y isn't defined like this. You can see that it's the determinant of fxx, fxy, fyx, and fyy, right? So this minus that gives you d as indeterminate. So it's the determinant of the Hessian matrix. And yeah, and what you want is positive definite versus, I mean, look, it's a whole big theory in higher dimensions. It's already complicated enough in R2. Let's not worry too much about this. Although Professor Drury really did like the Hessian and would often ask questions on the final about it, we're not going to go past the two-dimensional case. Understand that it does extend to higher dimensions through the Hessian matrix. You can look that up if you're interested. But let's go back to the saddle point issue. And what is this? This is 2 times -2 minus 0 squared. The whole thing is -4, which is less than 0. So according to this, we have a saddle point at the origin. All right, very nice. That still doesn't answer the question, what is a saddle point? Well, at least we now know that we have one at the origin. Let's graph this function. What does that function look like? So what are we graphing? We're graphing z equals x squared minus y squared. Well, you know what that looks like in the xz plane. When y is 0, z is x squared. This is just a parabola. Right? Easy enough. And in the yz plane, z equals negative y squared. Well, this is just a parabola coming down. And now, if you cut it at particular values of x, so if you look at the level curves for x equals c instead of x equals d, instead of z equals c, right? What are we looking at? Z is c squared minus x minus y squared. It's a parabola coming down from this one. So at the origin, I mean, what does this look like? This looks like exactly a saddle that you would ride a horse with. And that's what a saddle point is. In one direction, the function is increasing. And in the other direction, the function is decreasing. How are we doing? Let me leave this here while we do a few examples. Convinced? Let's take a few questions from the book. We are asked to find local max, min, and saddle points. right? I mean, it's a good name. It's a good name, very descriptive of what's happening. Yeah, certainly, and I invite everyone to have a look at a nice picture. I mean, because my graphing skills are very bad, but just go to Juan's suggested website or any other and graph the function we were looking at, x squared minus y squared, and you'll get a very nice 3D graph of what's happening. But let's move on to this. The question is asking us to find local max, local min, and saddle points. You know what to do, right? We're going to look at the partial derivatives with respect to x and y and find where these are equal to 0 so we can use a second derivative test to classify. Needless to say, right, this doesn't tell us what happens when d is 0. And if d is 0, the test is inconclusive. Derivative with respect to x. Derivative with respect to y. And we wish to work out where these are equal to 0. Two equations, two unknowns. You can use matrices or whatever you want to solve. I mean, from here it's easy to see that x is 2 plus 2y. And if you plug it into the next one, to the previous one here, we have y minus 2 minus 2x. And x has just been found to be 2 plus 2y. So y minus 2 minus 4 minus 4y. And minus 3y is equal to 6. Y is equal to minus 2. And if y is minus 2, x is also minus 2. Looking good. So once again, we only have the one unique critical point, minus 2, minus 2. You'll see that in working things out, you may get more than just one critical point. You may get several. You may get infinitely many. It depends on the question. But let's, again, I don't want to erase that quite yet. Let's move on to fxx. The derivative of this with respect to x. fxy. Derivative of this with respect to y is just 1. And fyy is minus 2. Again, just constants. Normally, you're going to get functions of x and y. So that it's going to be important to plug in the actual points. Here, d fxx times fyy minus this squared, 4 minus 1 squared is 3, which is bigger than 0. So now it's going to depend on fxx. And fxx is less than 0, so we have a local maximum. So we have a local maximum at that point. Let me rewrite it here. So if D is bigger than 0, and fxx is bigger than 0, local max. If D is bigger than 0 and fxx is less than 0, local min. And if D is less than 0, saddle point. Will we always be able to tell if fxx is greater or lesser than 0 if it's a function? Remember that it's at the point, right? I think Aisha suggested that it's at the point AB. So why doesn't it depend on fyy? You could, Shian is absolutely correct. You could reformulate the entire thing in terms of fyy as well. Yeah. D is fxx fyy minus fxy squared. All right, let's try 12. Same question, different function. There it is. So partial derivatives with respect to x. Partial derivative with respect to y. So you see here, if I factor out a minus 4x, I am left with x squared minus 1. Which factors is this? So critical points, what do we have? Here x could be 0, 1, or minus 1, but y has to be 0. So in this case, we have the 3 points, 0, 0, 1, 0, and minus 1, 0. Right, so now we have 3 separate points to check. Let us look at fxx, which is minus 12 x squared plus 4, fxy, which is 0, and fyy is minus 2. All right. So what? So what is your D? Your D here is going to depend on the actual point. So D at the origin, right, when x is 0, that's going to be 4 times minus 2 minus 0 squared, which is minus 8. So D is negative, so we have a saddle point at the origin. At the point 1, 0, that's going to be minus 8 times minus 2. So that's 16, which is bigger than 0. Now it depends on fxx. And fxx at 1, 0 is minus 8, which is less than 0. So local max. At 1, 0. And finally, at minus 1, 0, or D of minus 1, 0, well, that does not make a difference. And fxx at minus 1, 0 is also minus 8, which is less than 0. So again, local max. Questions? Everybody comfortable with this? The question arises naturally. I mean, here we're doing local max and min. What about absolute? What about absolute max and min? Well, I mean, maybe we want to start with the definition. Let f of x, y be defined on a domain D. So a saddle point has no defined derivative. What does a saddle point mean conceptually? We drew the first example we did, right? We drew what was happening. And at a saddle point, locally, the function looks like a saddle. Right, so in other words, in one direction, in the x direction here, if you move in the x direction, your function increases. And if you move in the y direction, your function decreases. That's what's happening at a saddle point. Is it always the case that it looks like a saddle? Yes. At least very, very, very locally. Well, I mean, the idea is that in one direction, in one direction you're increasing, in another direction you're decreasing. Right? Because remember that we are only looking at fxx. I mean the derivative in the x direction and the derivative in the y, right? So yeah, that's what's happening. So increasing in one, decreasing in the other. Let fxy be defined on a domain D. We say f has an absolute maximum. Has an absolute maximum point A, B, and D if f of xy is less than or equal to f of AB for all xy in the domain. In other words, your function never gets larger than what it is at AB. Absolute minimum, similarly. Now think back to Cal 1, right? Because I mean, we have a lot of experience with the Cal 1 scenario. And you had this nice theorem about the existence of an absolute max and an absolute min. In Cal 1, if f is continuous on a closed and bounded interval, interval AB, then f has an absolute max and an absolute min in AB or on AB, whatever. In other words, there's a point where the function never gets larger than what it is. This theorem extends. Theorem, if f of x, y is continuous on a closed and bounded domain. On a closed and bounded domain D, then f attains an absolute max and an absolute min in that domain. Exactly the same thing as here, as the Cal 1 counterpart. Well, think back to Cal 1. Where did the absolute max and absolute min occur? Where can they occur? In Cal 1, the absolute max and min, can only occur at critical points or endpoints. Right? These have to, thank you, Benjamin, these have to occur at critical points or endpoints of the interval. The same idea occurs here. The absolute max and min can only occur at critical points or, now D doesn't have endpoints. What D has, right, D is some domain in the xy plane. D doesn't have endpoints because it's on an interval. But what D does have is a boundary. And these must occur, the absolute max and min, at critical points or on the boundary. Right? The boundary is what limits D. It's what you have to cross to get from inside of D to outside. Well, it's not that the function must be on a closed and bounded interval. It's that if it is on a closed and bounded interval, then it must absolutely have an absolute max and an absolute min. If the interval is not closed, it may or it may not. And same thing here. If you have a closed and bounded domain, the function and your function is continuous, then it must achieve an absolute max and an absolute min. If your domain is not closed and bounded, then it may or may not. Well, we have, why is that? Nicholas is asking, why is that? And we have immediate counter examples. And let me give you an immediate counter example. A very simple example. F of x is x on the open interval 0, 1. Right? Let's just graph that. You know what the graph is. Starts at 0, goes all the way to 1. It's a straight line. But it does not include the endpoints. Right? Because 0 is not included and 1 is not included. So this function, f of x equals x, is bounded above and it is bounded below, but these bounds are not attained. Right? And if you take any point less than 1, then it's not going to be an upper bound. So this function does not attain its maximum. There is no maximum attained on the open interval 0, 1. And there is no minimum attained. Right? I mean, you can get as close as you want to 0, but there's always a number smaller that it attains. However, if you close it up, if you close up the interval 0, 1, then f of 1 is 1, and x is less than or equal to 1 for all values on that interval. And similarly, it's less than or equal to 0, and the minimum is attained as well. So it attains its absolute max, and it attains its absolute min. And the problem here is that your interval was not closed. If you close it up, continuous function on a closed and bounded interval, we're good to go. It attains an absolute max and an absolute min. If the interval is open, here it doesn't. But if you take a function like this, so I mean, suppose still that on the interval 0, 1, something that looks like this, then it will attain an absolute max, but not the absolute min. Or if you do vice versa, then it attains its absolute min, but not absolute max. Or if you have something like this, what do I want? then this function, even though the interval is open, this function attains its absolute minimum and its absolute maximum, even though the interval is open. So it's not an if and only if statement, but if the interval is closed and your function is continuous, it must attain an absolute max and an absolute min. One is saying if the absolute max is attained at 2 points, do we say it has 2 absolute maximums? We do not say that. It has just the 1 absolute maximum, but it occurs at 2 different places. And I stated the theorem in the xy plane, but of course it extends to higher dimensions as well. If you have a function in higher dimensions, if it's continuous on a closed and bounded domain, it attains an absolute max and an absolute min. And once again, where can these occur? At critical points or on the boundary. Let's take an example. We are asked to find the absolute max and min on the domain D, where the function All right. Let's take a moment to graph this to understand what's happening. We have the origin. When x is 0, y is 2. And when x is 4, y is 0. So this is the triangular region, closed and bounded. Well, perhaps you're wondering, what does closed and bounded even mean? We did not address that. Bounded means you can draw a circle around it. In other words, it doesn't go off to infinity in any direction. Closed means it's not open, in the sense that everything is included. You don't have dotted lines here, right? Everything is included in this region. As opposed to triangles with dotted boundaries, where the boundary would not have been included, right? You could have gone as close as you wanted. Well, look, it's really the same thing as the interval 0, 1 versus the open interval versus the closed. This includes the boundary, So here, closed means including the boundary. That's a better definition. For us, at least. So bounded means you can draw a circle around it, which you can. And closed means it includes the boundary. All right, so there you go. We have a closed and bounded domain. And we have a polynomial in x and y. So really, a continuous function. So this must attain an absolute max and an absolute min. Where can these occur? These can only occur at critical points or at the endpoints or on the boundary. So let's start with critical points. Start by taking the derivative with respect to x. 1 minus y. Derivative with respect to y. 1 minus x. So these are defined everywhere. So critical points are going to be where these are equal to 0. And it's easy to see that the only critical point is the point 1, 1. Question: is the point 1, 1 in the interval? In the domain, rather? Maybe, maybe not. It's not clear. Maybe we should work out what this line is. And this is easily seen to be a line with slope. Slope what? You go down 2 y's when x is 4, so slope. Change in y divided by the change in x, slope negative 1/2. With y-intercept at 2. Is that right? When x is 0, y is 2, looking good. And when x is 4, y is 0, perfect. And now when x is 1, this is 1.5. So you know that the point 1, 1 is inside. So this point 1, 1 is in the domain. Excellent. Now let's look at the boundary. The boundary is made up of 3 line segments. Let's call them C1, C2, and C3. C1 is a piece of the y-axis, or a piece of the line x equal to 0. Where y varies between 0 and 2. So on C1, your function, when x is 0 and y is y, your function is just y. So now we want to maximize and minimize this on the interval 0 to 2. Well, now this is just a function of one variable. So you know how to maximize a function of one variable. Now we're in a Cal 1 situation. You can take the derivative. Right? And when you take the derivative is 1. So no critical points. So the maximum must occur at the endpoints, max and min. So f of 0, 0 is 0. F of 0, 2 is 2. This is the minimum. and this is the maximum. And repeat on the other two line segments making up the boundary. C2 is part of the x-axis. So y is 0. And x varies from 0 to 4. So your function, when y is 0, what do we have there? We have just x. And again, you know what's going on there, right? The derivative. So no critical points. So max and min must occur at the endpoints. F of 0, 0, 0. F of 4, 0 is 4. This is the min, this is the max. And on C3, well, this is part of the line segment, y equals minus 1/2 x plus 2, where x varies from 0 to 4. I suddenly wish I had not erased that, but it's too late. What is the function when x is x and y is minus 1/2 x plus 2? I believe our function was x plus y. Minus xy. Is that right? Thank you. So this is 1/2 x plus 2 plus 1/2 x squared minus 2x, or 1/2 x squared minus 3 over 2x plus 2. And we want to maximize and minimize that on the interval 0, 4. So d by dx of this so look at critical points. This is x minus 3 over 2. So critical point of 3 over 2, which is in the interval. And now we just have to look at f when x is 0. So f of 0, 2. So when x is 0, y, well, so when x is 0, the whole thing is 2. When x is 4, when x is 4, this is 0. And when x is 4, what do we have here? 8 minus 6 is 2 plus 2 is 4. And finally, when x is 3 over 2, this is minus 3 over 4, so that is 8. So that's 5 over 4. And when x is 3 over 2, what do we have here? 9 over 8 minus 6, so that's 2 over 8. That's 1/4. 1/4 plus 2. 9 over 4. I want to say 9 over 4. Somebody verify that. 9 over 4. All right. And we also had to check the function at the point 1, 1, which was 1 plus 1 minus 1. And now the maximum of all of these values is apparently 4. Right? And the minimum of these values is seemingly 0. The point 1, 1 did not bring anything good. So let's state that. Maximum of 4 at the point 4, 0. And minimum of, do we say 0? Minimum of 0 at the origin. Convinced? How are we doing? That's my question to you. Is that correct, Nelson? Why did we have to check all these points? Well, the theorem tells us that the maximum can only occur at critical points or on the boundary. Yes. Exactly. Exactly, Nelson. Well, I mean, that's what I believe, unless I've made a mistake. So that's where I'm asking you to check. So the original critical point doesn't hold up because we cut this function at some slopes heading lower or higher. Exactly that. Oh, Nelson is getting a different answer. Maybe the 5 over 4 was incorrect here. When x is 3 over 2 on this line here, this is 3 over 4. That's 5 over 4. So you get 3 over 2 plus 5 over 4 minus the product, 15 over 8. So that's 12 plus 10 minus 15. That is 7 over 8. You're right, 7 over 8. Why was I getting something else? I see my mistake. This was 9 over 8 minus 15 over 8. So that was a minus 6 over 8. Uh-oh. Plus 2. I'm getting 10 over 8 here. What is going on? Does anybody see the mistake? So there's a mistake somewhere. Oh, I see it now. 30, no. All right, well, anyways, I mean, there seems to be a slight mistake somewhere. I'm not finding it, but let's go with the 7/8. Let's, shall we do one more? Same question. Let me give you a moment to graph that, and let me see if I can find the mistake here. Seven over 8 it is. Finally found the mistake. 7/8. All right. We're good. Did you graph this? What is this? X squared plus y squared less than or equal to 3. You know that to be a disk of radius 3. Right, so it's the whole inside, but, right, so the whole inside because of the less than or equal to, and then not radius 3, but rather radius root 3. And we are, why did we minimize, maximize the border? Didn't we want to minimize, maximize f? I claim that's exactly what we did. We did not minimize and maximize the border. We minimized and maximized f on the border, right? F on the border. Here, your domain, again, restricting your attention to bigger than or equal to 0. So it's just this thing. Right? I mean, we had split up our border, if we come back to this question before I erase everything, we had split up the border into three pieces, C1, C2, C3. And we were looking at the function on the border, because the maximum and minimum can only occur at critical points or on the border, on the boundary. So the boundary was made up of three pieces, and we looked at each piece separately. So we're looking at the function on the boundary. That's what's happening. Now consider this. Again, all I've drawn here is the domain, right? You understand that there's a function hovering above, right? This function is hovering above in the third dimension, and we are asking, what is the maximum this function attains when you restrict your attention to this domain? What is the minimum the function attains? Because it's a continuous function on a closed and bounded domain, so it must attain an absolute max and an absolute min, right? It's bounded because I can draw a circle around it, and it's closed because it includes the boundaries because of the equals signs. So let's find the critical points. Derivative with respect to x, derivative with respect to y. Critical points are where these are going to be equal to 0. So when is this equal to 0? Well, from the first one, we see that y has to be equal to 0. And if y is equal to 0, this whole thing is 0. So you see there are no conditions on x then. X can be anything. So as one suggests, it has a critical line, if you will, where this whole part of the x-axis is a critical point. So critical points, x0, where x can be anything from 0 to root 3. You have infinitely many critical points here. Now, once again, the boundary is made up of three pieces. This straight line segment, let's call it C1. This straight line segment, let's call it C2. And this quarter circle, let's call it C3. So C1 is part of the y-axis. So x equal to 0. And y can vary. Y can vary from 0 to root 3. So your function, when x is 0 and y is allowed to vary, well, the whole thing is 0. That's nice. There's nothing to do here. All points are maximums. All points are minimums. The function is constant. Very nice. C2, here, y is 0. And x is allowed to vary. Again, between 0 and root 3. function when y is 0, well, again, the whole thing is 0. Certainly cuts our work down by quite a bit. There's no thinking. Every point is a max, every point is a min. We're good to go. And notice that this also takes care of the critical points that we had before, right? Because they all fall on C2. So now, what about C3? How do we describe this curve? Well, I mean, it's part of the circle. So this is part of the circle, x squared plus y squared equal to 3, or y is plus or minus the square root of 3 minus x squared. But you understand that it's the positive square root, right? Because it's on top of the x-axis. Exactly. Nicholas has suggested that we could have looked at the function a little more closely and said, well, when x and or y is 0, the whole thing is 0, and that's exactly what C1 and C2 are. Absolutely. So now C3, this is part of the circle, the top half of the circle. So y is the square root of 3 minus x squared, where x goes from 0 to root 3. So your function on that curve, on that part of the boundary, when x is x and y is 3 minus x squared. What is that? Well, so that is x times root 3 minus x squared, the whole thing squared, or x times 3 minus x squared, or 3x minus x cubed. And now we have to ask the question, where is this maximized and minimized in that domain? Right, so let me call that G. So we're maximizing this on and minimizing on the interval 0 to root 3. Where do the max and min occur? Well, you know what to do. We're going to take the derivative. You take the derivative, you find your critical points, and so critical points, x is plus or minus 1, but negative 1 is not included in here. So that's out. And you only have the one critical point, x equals 1. And when x is equal, so maximum must occur at critical points or the endpoints. G of 0 is 0. G of 1, when x is 1, this is 3 minus 1, which is 2. And G of root 3 is 3 root 3 minus 3 root 3, which is 0 again. So you see what's happening. i.e. your function has a minimum of 0 where? On the x and y axes. And a maximum of 2 at the point when x is 1, y is root 2. There it is. On that part of the circle. Exactly here at 1 root 2. How are we doing? Questions? Well, here's what about the infinite critical points? We already took care of that. The infinite critical points were actually taken care of right here on C2, because C2 and the infinite critical points actually overlapped, right? They were the same thing. So by taking care of C2, we actually did all the critical points as well. But you're certainly welcome to do them separately, and when y is 0, the whole thing is easily seen to be 0. Now the question, why is it root 2? Well, I mean, we know it's on the circle, right? It's on C3, and it occurs when x is 1. So when x is 1, y is root 2. F has a minimum of 0 on the x and y axes as well as on C3. Well, on C3, where does it occur? It occurs at the endpoints. So on C3, 0 occurs right here, which is also part of C2, right? It's where they meet up. And right here, where C3 and C1 meet up. Yeah. All right. So the question arises, right? I mean, here, a continuous function on a closed and bounded domain achieves an absolute max and an absolute min at critical points or on the boundary. The question, why did we check g of 0? Well, I mean, you're trying to maximize and minimize this function on that closed and bounded domain. Yeah, that's fair. So, what we did was we found the critical points, and then we considered the boundary by describing every boundary. By describing the boundaries, every piece of the boundary. The question arises, surely there must be an easier way to check the boundary without having to describe it. And there is. We will see that tomorrow. So tomorrow we're going to see another way to consider the boundary without having to describe it as y equals something and doing all of this work. All right. Thank you all for coming, folks. We'll pick this up again tomorrow. with a method known as Lagrange multipliers. Thank you all for coming. I will see you then.